In the previous video, I had left you with this expression over here. I'm going to move on and talk about the shear stress profile and the velocity profile for a turbulent flow. But before that, I want to address a couple of questions here that you may have or that you may have been thinking about. The first is that you may think that could we use this equation for a laminar flow as well? Well, yes, we can, because you see that fluctuations for the x component of the velocity profile or the y component of the velocity profile, they don't really occur in a laminar flow. So that means that they would be equal to 0 here. And that means that if these two were related with each other and an average was taken of these two quantities, which is being shown by the bar here, that would be equal to 0 as well. And that means that this entire term is going to be equal to 0, and we are going to be left with this expression, which is the same one that we've looked at already for the laminar flow. The second question that you could have is that, hang on, this quantity over here is negative. So does that mean that if we are looking at the turbulent flow, then the total shear stress is going to be a smaller quantity as compared to if we were just looking at the laminar flow? Well, no, that's not true either, because it turns out that this entire quantity is actually positive. So that means if we're looking at a turbulent flow and we would have some kind of positive value here, that means that this entire term is going to be higher in value as compared to if we were just looking at the laminar flow. Okay, so in the case of a turbulent flow, the shear stress is higher as compared to a laminar flow. And now the thing is that although the relative magnitude of this laminar shear stress and this turbulent shear stress, the structure of these two, the magnitude of these two is complex, and it's a complex function, and it is dependent on the specific kind of flow that would be involved. But we have a structure that can give us a lot of accurate information if we were to look at the shear stress and the average velocity profile for a turbulent flow. So what this indicates here is that we divide or we subdivide the velocity profile for a turbulent flow in terms of different layers. And what do these layers indicate? What these layers indicate is that if you were looking at it in terms of the shear stress, this shear stress is basically a combination of the laminar shear stress and the turbulent shear stress. So if I was to look at how this shear stress is going to be related when we're looking at, let's say, the viscous sublayer. In the viscous sublayer, what we essentially see is that the laminar shear stress is important, right? Because if I was looking, let's say, over here within this region, okay, which would be somewhere between these two regions, what this means is that this entire thing is giving us the laminar shear stress, and then some small quantity here, some small value here, this is giving us the turbulent shear stress. So what does that mean? That the laminar shear stress is more dominant as we get closer to the pipe wall. Okay, this is your viscous sublayer. Away from the wall, when you're looking at the outer layer, as you move closer to the center line of the flow, okay, as you move into the outer layer, what you discover is that the turbulent portion of the shear stress is dominant. How is that so? Well, let's say if you move on somewhere here, this entire thing is the turbulent part of your shear stress, and this small detail here is going to be your laminar shear stress. Okay, so as you move away from the wall, the turbulent shear stress becomes more important. Okay, so the turbulent shear stress is more dominant. As you move closer to the wall, the laminar shear stress is more dominant. And then you have the transition phase between these two, which is called the overlap layer and the overlap layer. Both of these are important. So just to review here, this viscous sublayer is also called a wall layer. And over here, the viscous shear is dominant. In the outer layer, the turbulent shear is dominant. And in the overlap layer, both types of shear are important. Okay. Now there's a couple of issues here that we need to look at in more detail. The first is the scale of the sketches that is being shown in these figures is not necessarily correct. What do I mean by that? Well, what I mean is that typically the value of this turbulent shear stress in the outer region is 100 to 1,000 times higher than the laminar shear stress. Okay, so this is much, much higher than the laminar shear stress when we're looking at the outer layer. So this doesn't just this dotted line here doesn't do justice to how big of a factor that is. It's actually very, very small, very minute here. Okay, but just for visualization's sake, so you could see better, this is how it's represented. And it's the same over here as well. As you move closer to the pipe wall and the viscous sublayer, these laminar shear stresses are so much more dominant and of a much higher order as compared to the turbulent shear stress. Okay, so this is one thing that we need to be careful about. The second is that this vertical scale is very distorted as well, because this viscous sublayer, the thickness of this viscous sublayer, this is not how it is. It's actually very, very small, extremely small, just very, very close to the pipe wall. And just to give you an example, if I had let's say, a pipe here with a 10 centimeters of diameter and the velocity of the flow was 3 meters per second, the viscous sublayer would be of the form of 10 to the power minus 3 centimeters, okay, within a 10 centimeters diameter of pipe. So you can go ahead and see what percentage that is of the total pipe diameter, and you will see how small this percentage is, how small this thickness is. Okay, so these two things are really important to consider, but at the same time, this does not mean that the viscous sublayer is not important or that we can neglect the laminar shear stress here. Why is that? Because this is probably the most important layer that we're looking at when you're looking at the pipe wall, because not only do you have the wall shear stress that is happening at the wall and at the inner layer, but also the no-slip condition that you apply, that the velocity is 0 at the pipe wall, that is within this viscous sublayer. So that means that in order for us to truly be able to find out what is happening to the flow characteristics, we need to find out what is happening within the viscous sublayer. And what that means is that because the thickness of this viscous sublayer is so small, then that means that it is highly dependent on the geometry of the pipe as well. If the geometry is smooth, then you would get different kind of results. But if the geometry had certain dirt elements in there, scratches in there, any roughness elements in there, then that could easily basically disturb this viscous sublayer and the flow properties within it, and that would mean that the entire flow would be affected by it. Okay, so this viscous sublayer is important, and it's important to understand that this is why a turbulent pipe flow is extremely dependent on the roughness of the pipe wall. Okay, so I'm going to move on now and try to express the equation that we previously looked at for this variable here, which is the turbulent shear stress, because we said that well, this is just to show you that same thing with both pipe walls indicated here, so you could have better visualization of how this variation between the turbulent and the laminar shear stress looks like, and how the velocity profile looks like. And the velocity profile remains constant within a fully developed turbulent flow as well. I'm going to move on now, and I'm going to quickly look at this equation. Previously, we had this equation for the turbulent shear stress in the form of rho and fluctuations in the x component and the y component of the velocity profile. Turns out that this entire thing, it's hard to find out and accurately determine what these Reynolds stresses are. Because they're changing at every instant. They're changing in time as well. These fluctuations are varying over time and space, so it's hard to accurately determine what these fluctuations are. So instead of using this form of the equation, we move on to using this terminology, and this was introduced by a really important name in fluid mechanics, Boussinesq. And he gave this concept of eddy viscosity here. This is called eddy viscosity. And this is not like the absolute viscosity that we look at. The absolute viscosity here, it's a known value for any fluid. Like for water, let's say, if I told you to go ahead and check out the value of absolute viscosity for water, you could just go into one of the tables and find out that value. But this eddy viscosity here, you cannot really go ahead and find it out like that, because the eddy viscosity is a function of the fluid and the flow conditions. So what that means is that the value of this eddy viscosity here, it changes from one turbulent flow condition to another. And not only that, but it also changes from one point in a turbulent flow to another. Okay, so then, well, we could say that what is the point of it then? Because if we can't determine this expression, if we cannot determine the Reynolds stress here, and we cannot determine the eddy viscosity here, then why replace it by that? Well, that is what all of these theories are about for turbulent flow. They don't have that exact mathematical expression behind them, but we go with semi-empirical theories, we go with approximations to find out something that we see through observation or through experimentation that is working for us. So then basically this expression is something that is one of the models that is suggested for turbulent flows. There are different models, and this is one of the models that is suggested by Boussinesq. And then Prandtl worked on this model and basically went with eddy viscosity and went ahead and found out this eddy viscosity in terms of something called the mixing length here. And well, mixing length can be used to basically find out the eddy viscosity here. But what we find out is that even the mixing length from a one region of one velocity to another region of a different velocity, the mixing length varies. But by using some ad hoc assumptions, by using the physical reasoning, it was concluded that this mixing length is related to eddy viscosity by this expression. And then we can go ahead and substitute this over here in the expression for turbulent shear stress. And this is what we find out. So instead of now trying to find out the eddy viscosity, we are trying to find out mixing length here. But it turns out that, again, this mixing length is not constant in the flow field either. Okay, because near the pipe wall, the turbulence is dependent on the distance from the surface, so we make more assumptions and more assumptions on how this mixing length varies throughout the flow. So the result is that there is no general useful model that can be used to accurately predict the shear stress. But that does not mean that we can't study turbulent flow, and that does not mean that we cannot have models that can give us good, highly accurate solutions, highly accurate approximations to find out solutions. Because it turns out that these models can be applied to, let's say, certain instances. So, for example, one model would be only applicable in the viscous sublayer, and it would not work in the other two layers. Or one model would be only applicable in the outer layer, and it wouldn't be working in the other two layers. So this is how we make do with what we've got. No general useful model, but different kinds of models exist that can give us different kinds of approximations to find out highly accurate solutions. Okay, so just moving on from this now, I'm going to move on now and talk about the turbulent velocity profile. And again, just to review, the viscous sublayer, when we're talking about the viscous sublayer, let's just look at this here. When we're talking about the viscous sublayer here, the viscous shear stress is dominant as compared to the turbulent shear stress. When we're talking about the outer layer here, the turbulent shear stress is dominant instead of the viscous shear stress. So the character of the flow within these two regions is completely different. What do I mean by that? That when we're looking at the viscous sublayer, what is important? The fluid viscosity is important here, and density is not that important. Why not? Because we're not moving huge chunks of finite particles in the viscous sublayer. And similarly, when we're talking about the outer layer here, density is more important of a factor as compared to the viscosity. So by using different approximations, by using different dimensional analysis arguments for the flow, there have been possible conclusions that have been found for the turbulent velocity profile. And so we find out that in the viscous sublayer region, using dimensionless forms, we can actually relate the average velocity to different terms here. And over here, this y term here represents the distance that is measured from the wall, and this u star term here represents something called the friction velocity. And this is not actually velocity, it's just that it has the same dimensions as that of velocity. And what's important to understand here is that if we know, let's say, these two dimensionless terms, then we would be able to find out the velocity profile within the viscous sublayer region. And usually this side of the expression is denoted by something called u plus, and this side of the expression is denoted by something called y plus. And this expression is only valid for a y plus value of 5 or less than 5. We're going to just look at that in a second in a graph. But for the overlap layer here, we have another equation, another expression that is going to give us the solution for it. And that is, again, in terms of the same two dimensionless quantities, u plus and y plus. It's just that the form of the equation varies, it differs. So if I was to look at, let's say, a pipe here, and we're looking at, if I was to represent the pipe here, I'm looking at the pipe vertically. So this is my pipe wall. Okay, this is my pipe wall here, and the center line of the pipe is indicated here. So this is my center line of the pipe. And what this shows me is that this is obviously, where is the viscous sublayer going to be? It's going to be closer to the pipe wall. So this is my viscous sublayer. And this equation, it's also called the law of the wall because this is next to the wall. So this equation is only valid here. It's only valid for the viscous sublayer. Okay, do you see that? That if we try applying the same equation, it wouldn't work because experimentally we see that this is not how these two dimensionless products are correlated. Okay, it just doesn't follow the same pattern in. So this is only valid, this equation is only valid for the viscous sublayer, and then this equation is valid over here for the overlap region. Okay. Now the same thing is being represented here by this expression. And then if we move on, we can also find out the outer layer expression as well, and that is given by this equation. And over here, this value of n is basically dependent on the Reynolds number, and if n is, let's say, 7 or higher than that, then that is a reasonable approximation that you can use for many practical turbulent flows. And this is the power law velocity profile correlation. And it's an empirical correlation. Again, this is not an equation that is determined mathematically. It's determined based on experiments and physical reasoning. Okay. So these are three major layers that we look at within the turbulent flow. And I'm just going to go ahead and talk about turbulence modeling. I'm not going to go into the details of it. I'm going to leave you a link here that will take you to another video that would be able to explain turbulence modeling if you're interested in that. I'm going to restrict myself to only the basics of it that we've just talked about. There's different kinds of turbulence models that exist. There's something called the Spillard-Allmars model. There's something called K-epsilon model, K-omega model, K-omega SST models. So these are just names that I'm mentioning here so that maybe you can go and look them up yourself and try and see what they're all about. I'm also going to leave you a link here so you can go ahead and look at it in your own time and see what turbulence modeling is about if that is something you're interested in. Now I'm going to leave you with a few questions here, a few review questions that you can go through and basically try to make the understanding of what you've looked at in these two lectures a bit better. Just go through these questions and let's say this x, the diameter here could be, let's say, equal to 0.1 meters, let's say. Okay, it could be equal to 0.1 meters. So just go ahead and try and answer these questions and try and work out this numerical problem too, so you obtain a better understanding of what turbulence flow is about.